let's talk about a very nice fact about nilpotent matrices that helps us find the nilpotent index of a matrix. Let's just go back a little bit and remind ourselves what is the meaning of a nilpotent matrix. We're talking about a matrix that is square, that when there is some integer, some natural number, in this case k, such that if I take a and raise it to the power of k, I will get 0. This is by definition tells me that this square matrix A is a nilpotent matrix. Now, sometimes it's not the easiest thing to find the nilpotent index of a matrix, because if you think about the very difficult matrices, in order to find an nilpotent index, sometimes you need to multiply again and again the matrix by itself until you get to a certain power by which the matrix becomes 0. It's not the easiest thing all the time. So what is the nilpotent index? Maybe I should also say that by Cayley-Hamilton theorem, you know that the characteristic polynomial of a matrix annihilates the matrix. So the characteristic polynomial of a nilpotent matrix x is x to the power of the order of the matrix. So you do know that there is an upper bound to what can be the nilpotent index, which is the power of the characteristic polynomial. Of course, if you find the nilpotent index, you will also know the minimal polynomial of the matrix, because this is the minimal polynomial that annihilates the matrix, and it will be x to the power of something, which is less or equal the characteristic polynomial power. But we need a way, an easier way sometimes, to find this minimal index that annihilates the matrix, the minimal index that when you raise the matrix to its power will give you 0, the nilpotent index. Now, again, multiplying a matrix again and again is an option, but not always very easy way. And so using the Jordan canonical form that must have two nilpotent index, the reason that every nilpotent index, at least above the reals, should have and have a Jordan canonical form is from the fact that the characteristic polynomial is x to the power of the order of the matrix. Let's call it n. And for every matrix that the characteristic polynomial can be factored into linear terms, we are guaranteed that this matrix with this characteristic polynomial have a Jordan canonical form, as the characteristic polynomial of a nilpotent matrix must be x to the power of the order. We know that x to the power of the order of something is linear terms multiplied, so every nilpotent matrix has a Jordan canonical form. So we can look on the Jordan canonical form. So here it is. A is similar to some Jordan canonical form with Jordan blocks. You see that I have, for example, here the first block, the second block, the third block, and etc. etc. Now, for a Jordan canonical form for eigenvalue 0, and all the eigenvalues of A are 0, so all the blocks are of eigenvalue 0, we know that the nilpotent n index for such Jordan canonical form is just the size of the biggest block. You can calculate it, and I did a video on the binom, how binom can be used to calculate and raise to the power of something in a Jordan block. But anyway, I'll just tell you now that the nilpotent index of each of those Jordan blocks is just its order. So all I need to do, and remember that the nilpotent index is preserved on similarity. So the nilpotent index of the similar Jordan form of A is the same nilpotent index of A itself. So the nilpotent index of the Jordan form is just the size, the order of the biggest Jordan block in the Jordan canonical form, and that's it. So when you get to the Jordan form, very easily. You just look on the biggest block, and this is it. This is the nilpotent index for a nilpotent matrix. So the index of A, the nilpotent index of A, is just the max value from the sizes of the blocks in the Jordan canonical form. That's it. Very immediate, very nice. Just look on the Jordan canonical form, find the biggest block, and this is the nilpotent index for a nilpotent matrix. And remember that the Jordan canonical form, similar to a matrix A, nilpotent matrix A, always have blocks only for the eigenvalue 0 because A, the nilpotent matrix A, every nilpotent matrix has only eigenvalues that are 0. All of the eigenvalues are 0. Therefore, all the blocks of the Jordan canonical form that is similar will be for the eigenvalue 0. Therefore, they are nilpotent also. Thank you very much. That's it. This was how we can use the Jordan canonical form to find the nilpotent index easily of a nilpotent matrix. Thank you very much. Thank for JGPT for writing it down neatly, and thank you all for watching. That's it.